All right, in this video, we're going to start out sketching some polar graphs. So we've already converted to rectangular equations. And so I'm not really interested in sketching graphs that we've already done, we've already converted into rectangular equations. I'm going to be interested in sketching some polar graphs that usually you cannot easily solve in terms of rectangular form, okay? So things like this, r equals 3 plus 7 cosine theta. Now, let's take this equation here. By the way, usually when you're dealing with polar equations, usually we like to write r equals a function of theta, just like when we were dealing with um, rectangular equations. A lot of times we solve them for y, so y is equal to a function of x. Polar equations usually have this r equals a function of theta. So let's focus on this one. R equals 3 plus 7 cosine theta. Now, instead of just plugging in different values for theta and seeing what happens, what I'm going to do is I'm going to utilize my calculator. So you could, in fact, plug in different values for theta and, do the points and plot it out. But it's a lot more efficient to just use our calculator. R equals 3 plus 7 cosine theta. So if we do that, first off, we like to make sure we're in the correct mode. So hit the mode button on your calculator, go down to where we have function, parametric, polar, sequential, and make sure you're on the polar mode. Okay, some calculator versions have POL and PARA for parametric and polar, but mine has the word polar. Now, once you've done that, you can simply hit y equals. And if you hit y equals, what's going to happen is you're going to have a screen like this. It'll have R1 is equal to, and then I've already typed my equation in. Obviously, this is just a picture of my calculator screen because I can't do this on an overhead like I normally would in class. So 3 plus 7 cosine theta. And if you hit zoom and then standard or zoom square or something like that, you're going to be able to see this graph. And if I hit zoom, mine's in square, you get this. And if you watch carefully, you'll see this actually graph. It'll start here and it'll graph up, follow my cursor here, following my cursor over, get an inner loop, and then come around and hit. This is a special graph. I call it, say, Limacon or Limacon. You can read that in the book, but this is a Limacon with an inner loop. All right. There's other Limacons as well, but this one is with an inner loop, and you can clearly see this is not a function in the rectangular form. In the y equals a function of x, you couldn't graph this very well, but there you go. So that's how you graph with your calculator. Now you can also graph using things like Desmos and things like that. So y equals 3 plus 7 cosine theta will absolutely graph in Desmos as well. I've done that in the polar, and you can see the Limacon there. Okay. By the way, also Desmos allows you to go what values of theta you're between. So if, for instance, you went from 0 to, instead of 2 pi, if you went to pi over 2, you'd only get to there. And if you go to 0 to pi, you go all the way around to here, and then obviously you finish it if you went to 2 pi. By the way, if you went to 4 pi, You get the same graph, but all that happens is you start at 0, so you start at this point where my cursor is. It'd go around. We already see all pi over 2, pi. You'd come back around. This would be 3 pi over 2. You'd end up here at 2 pi. And then from 2 pi to 4 pi, you just retrace the graph again. Okay? So a lot of times you have that where we have these repeated cycles. So a lot of times when you graph, your window will be set from theta from 0 to 2 pi. If that's not, you can always hit the window button on your calculator and go theta min 0, theta max 2 pi. Now, some interesting things happen. Let me manipulate this a little bit. What would happen if I, instead of taking a 3, if I would have taken a 4? Well, that would have happened. It'd just be slightly reshaped. Or if I went from a 7 to a 5, notice that little inner loop got a lot smaller when 4 and 5 got closer to each other. What would happen if 4 and 5 were the same? Well, that inner loop would be eliminated. All right, this is called a cardioid when that inner loop just gets eliminated. So what happens is it starts here, goes around, hits this point, and around again. And if this 4 becomes less, the coefficient on the cosine becomes less, let's call it a 3, you'll see that as it dimples a lot less. By the way, this is called a dimpled limacon, basically. Okay, and you get a convex limacon if the ratio gets much smaller. So this is a convex limacon because it doesn't go back in. All right, so convex limacon versus a dimpled limacon versus a straight up limacon with an inner loop. See there. Okay, so that's what happens. Now, the next equation that I have you graph is 5 minus 5 sine theta. So I want you to see what happens, the difference between cosine and sine, and then what happens with the minus out here. So why don't you go ahead and do that? Graph r equals 5 minus 5 sine theta and see what you end up with. Push pause on the video if you would. All right, so hopefully you went ahead and did that. Get some weird stuff. There we go. Notice what's going on. 5 minus 5. I get that cardioid again. 0. I should do 0 to 2 pi. But you get that cardioid again. But now notice the orientation with sine. It's going up and down instead of left and right oriented. And by the way, change that minus to a plus. What happens? Oh, it flips what's going on here. So plus to a minus, minus to a plus. Okay, so it just flips around, whether it's sort of pointed up or pointed down, whichever way you think of this being pointed. So that's all the difference between sines and cosines. So same principle with sine, just things are pointed up and down versus left and right. All right, why don't you take your calculator and see what happens when you graph 4 sine of 5 theta and what happens when you graph 3 cosine of 4 theta. So graph those on your calculator and see what you get. When I graph 4 sine 5 theta, notice what's happening here. I'm going to get this petal figure. This is often called a rose curve. And this rose curve here has 5 what I call petals. So a rose curve with 5 petals, obviously rose because it looks kind of like a flower with 5 petals. There you go. And obviously, notice the coefficient here. The coefficient of 4 determined how far out each petal went. So it was out 4 units away from the origin at that petal's maximum value out. If you change that 4, let's say, to a 3, you only go out 3 units from the origin. If you change that 4 to a 7, now I'm going out 7 units from the origin. All right, so there you go. By the way, sine, I want you to notice real quick, I'm dealing with sine, and one of the petals is lined up directly on the line theta equals pi over 2. See that? The vertical line theta equals pi over 2, or what we would have called in the rectangular version, the y-axis. Now, if you change this around to cosine, so there you go, I just did that, 3 cosine 5 theta. If you change it around to cosine, notice that one of the petals is aligned with the polar axis, the line theta equals 0, or what we would call it in the rectangular version, the x-axis. So that's the difference between cosine and sine. One of the petals is lined up along the pi over 2, theta equals pi over 2 line with sine. One of the petals is lined up with theta equals 0 with cosine. Now, our equation that we were trying to graph was 3 cosine of 4 theta. Notice what happened. When we went from an odd to an even number, all of a sudden the number of petals doubled. So with 4 theta in my argument, I ended up with 8 petals. If I were to have typed in 6 theta, I would have ended up with 12 petals. If I were to type in 8 theta, I would have ended up with 16, and so on and so forth. 2, I end up with 4, etc., etc. And that has to do with periodic idea of pi, the arguments of cosine. That cosine and sine have this periodic argument where every time you go around 2 pi, you've gone around a circle once. So cosine is periodic of by a factor of 2 pi. In other words, cosine of A is the same thing as cosine of A plus 2 pi. Hopefully that makes sense. That's not something I'm going to quiz you on, but even powers, even rose petals, it's going to be it's going to have twice the number of petals that the coefficient of theta is. When we have an odd coefficient of theta, we have exactly that number of petals. All right. So those are a couple of different versions, how we write, how we can sketch polar graphs. Okay, again, use technology to do this. Use your calculator or use some computer software like I am. All right, so there you go.